Welcome to the method of Lagrange multipliers. I am Ronald Johns. Lagrange multipliers is a method used to solve optimization problems in calculus. They are also called max-min problems, finding the maximum or minimum of a function. The Lagrange multiplier method can be used when you have a function whose value is to be optimized, together with one or more constraints on the variables. It can also be used on functions of one variable or functions of several variables. And we can have more than one constraint on the function to be optimized also on the variables, a constraint on the variables. So let's look at an introductory problem to get a feel for what this method is about. Here's what we're going to have. We have a river, a straight river, and a farmer has 4,000 yards of fencing and wants to enclose a rectangular region along that straight river to keep his cows. So here we have that rectangular region that the farmer is going to build, and we're going to have some cows in this field. And let's let x be the width and y be the length of this rectangular field. So he has 4,000 yards of fencing. One side of the rectangle will be the river, so you don't need any fencing there. And the other three sides, we will use the fencing material. So what should the dimensions be to maximize the area of this field? So we want to find the values of x and y that will give us the largest area. And we have a constraint here. We only have 4,000 yards of fence. So let's rephrase this problem more mathematically. Let's let x and y be the width and length of the rectangular field. So here's the river over here, the rectangular field with a few cows in it, and the width is x and the length of the rectangular field enclosed by the fencing is y. And we want to maximize the area is a function of x and y, and for a rectangle the area is going to be x times y. We have a constraint. The total amount of fencing that we have is 4,000. If we look at this diagram over here, we have 2x from these two sides plus y has to equal the total amount of fencing that we have, which is 4,000. This constraint that we have is in the form a function of x and y equals a constant. In this case, 2x plus y equals 4,000. This is an easy calculus problem. You probably could have easily solved this in your first term of calculus. It turns out also that it's an easy multivariable calculus problem using Lagrange multipliers. We're going to look at this problem starting with the function of a several variable with a constraint, and we'll see the general ideas. And I'm not going to do many computations to start with, but later we'll see how we can fill in the missing details, the missing computations, so that we have a complete solution. So let's look at the ideas behind Lagrange multipliers. We want to maximize the area, which is a function f of x and y, which is x times y, length and width of that rectangular field the farmer is going to enclose. We have a constraint. We only have a finite amount of fencing, 4,000 yards of fencing along three sides of a rectangle. So 2x plus y has to equal 4,000. The constraint is that 2x plus y has to equal 4,000, and that's given by the red line in this diagram. A local maximum of f occurs where the constraint curve is tangent to one of the level curves, g of xy equals a constant. if we look at the graph, the plot to the right, we notice that the constraint curve, which is that red line, seems to have a point of tangency with the contour curve where the area equals 2 million. And that's about as big an area in square yards as we can get. That constraint line, that red line, does not intersect at all the 2.5 million square yard curve that we have for the area, nor any larger areas. So it seems that our answer is probably going to be we can have 2 million square yards enclosed with that amount of fencing along the river. Let's recall that gradients are perpendicular to tangent lines. So if we're looking at gradients instead of tangents to curves and tangents to lines, we'll be looking at perpendicular vectors to those tangent lines. So we could say then that more generally, it turns out, the maximum occurs at a point x0, y0, where the gradient of f is equal to some constant lambda times the gradient of g at that point x0, y0. Because one gradient is a constant multiple of the other, one vector is a constant times the other vector, and let's just assume for the time being that maybe it's a non-zero constant, then what we have are two vectors here that are parallel. So the gradient of f and the gradient of g are parallel at that point where the tangent line is tangent to that curve, the area equals 2 million. It turns out that the curve 2x plus y equals 4,000 is tangent to the contour x times y equals 2 million at the point x equals 1,000 and y equals 2,000. Let's recall that x and y were the dimensions of this rectangular field the farmer is enclosing with 4,000 yards of fence. So that tells us then from the diagram that we have on the right over here that the maximum possible area seems to be 2 million square yards. And if you look at the x and y coordinates of this point of tangency of this straight line and this curve where the area equals 2 million, the coordinates of this point are about x equals 1,000 and y equals 2,000. And so that would tell us then the dimensions of the field with the largest area. So let's ask if we have two gradients here that are parallel. One for the curve f of xy equals x times y, and the other one was the g of xy curve that we talked about earlier. So we want to maximize f with this constraint on the amount of fence that we're given. And if we look at the gradient of f at xy, by definition, this is the vector whose first component is the partial of f with respect to x, second component, the partial of f with respect to y. If we look at this first component, f is up here. If we differentiate x times y with respect to x, we just get y. For the second component, if we differentiate xy with respect to y, we get x. So then plugging in x equals 1,000, y equals 2,000 into this formula, we get the gradient of f at this point is the vector 2,000, 1,000. That's a vector starting at this point and going out in this direction. The direction of this arrow is correct, but its magnitude has been kind of normalized in this particular setup. So then let's look at the other part of this. This maximize and this function f, constraint that, same as up here. And if we look at the gradient of g at xy, which is the partial of g with respect to x, partial of g with respect to y for the first and second components of this vector. Let's see, g of xy is 2x plus y. If we differentiate this with respect to x, we just get 2. If we differentiate this with respect to y, we get 1. So the gradient of g is 2, 1. And so if we evaluate it at the point 1000, 2000, since this doesn't depend on x and y at all, it's still just 2, 1. So both curves go through the point 1000, 2000, which is right here. The gradient of f at that point was 2000, 1000. The gradient of g at that point was 2, 1. We notice that these two vectors are parallel. This vector up here is 1,000 times the vector down here. Those two gradients are multiples of each other, so those two vectors are parallel. So let's look at the method of Lagrange multipliers. How does this method work? Well, first, the problem that we'll look at is to maximize or minimize the function f of xy with constraint g of xy equals some constant. And then the method is to solve this system of equations. This is a vector equation, and this is a scalar equation. Two vectors are equal if they are equal component-wise. So what this gives us basically is two scalar equations for this vector equation, plus one more scalar equation. So this will be three scalar equations and three unknowns, the unknowns being x, y, and lambda. As an example, let's consider again the farmer problem. We wanted to maximize the area of a rectangular field, and if the dimensions are x and y, the area of the field is xy, so that's what we want to maximize. And we had a constraint, 4,000 yards of fence, and so we wanted 2x plus y to equal 4,000. Well, in that case, these are the equations that we want to solve. The gradient of f is equal to lambda times the gradient of g, and lambda is called Lagrange multiplier. And also g of xy equals 4,000, this constraint. So the gradient of f is going to be this vector. F, remember, is xy. So the partial derivative with respect to x of xy, that's just y. The partial derivative with respect to y of xy, that's just x. So that's what this gradient is. Moving on to the other side, lambda times the gradient of g is going to be lambda, and then the gradient of g is this vector. Partial derivative with respect to x of 2x plus y, partial derivative of y of 2x plus y. This partial derivative is just 2. This partial derivative is just 1. Lambda times 2, 1 is 2 lambda and 1 lambda. So then, if we look at this equation up here that we had with this particular f and particular g, that equation gives us that y comma x, this vector, has to equal 2 lambda lambda. Now, what is our system of equations going to be? Well, we're going to have the following. Y has to equal 2 lambda, x has to equal lambda, and those are these two equations. And the last equation is our constraint, 2x plus y equals 4,000. So let's continue the calculation. We saw that we have to solve these three equations, and so let's see what we can do. Let's start with 2x plus y equals 4,000. Well, up here we know that x is lambda and y is 2 lambda, So let's substitute those in. And so we have 2 times lambda plus y, which is 2 lambda, equals 4,000. We can simplify that to 4 times lambda equals 4,000. Divide both sides by 4, and we get lambda equals 1,000. And then we can come back up here and find the values of x and y. So x is lambda, which is 1,000. Y is 2 lambda, which is 2 times 1,000. That's y equals 2,000. And those are the dimensions of the field. Here's the river on this rectangular bounded field. This side is 1,000 yards. This length is 2,000 yards. And this width, again, is 1,000 yards. Often in textbooks, we may write the equations for the Lagrange multiplier method in terms of a new function. We'll call it capital F, and it's going to be a function of 3 variables, x, y, and the Lagrange multiplier lambda. And this new function is going to equal little f of xy, the function to be optimized, plus the Lagrange multiplier lambda times g of xy. And g of xy gives us the constraint, g of xy equals 0. So for this method to work correctly, we need the constraint that I just mentioned to be 0. For example, in the farmer's field problem, instead of writing the constraint as 2x plus y equals 4,000, we could write the constraint as 2x plus y minus 4,000 equals 0. So in this new formulation, our constraint function g of xy would be 2x plus y minus 4,000. So let's see what we can do. Once again, we're going to maximize or minimize f of xy, lowercase f, and the constraint we're going to use is g of xy equals 0. So what we're going to do is write the equations for the Lagrange multiplier method in terms of the partial derivatives of this new function, capital F of xy lambda, which is constructed from little f, g, and lambda. So we'll define capital F to be equal to f of xy plus lambda g of xy. And then let's see what happens if we take derivatives of capital F with respect to each of these variables. The partial of capital F with respect to x is the partial derivative with respect to x of all of this stuff. So here we have it. And so, using linearity of the derivative, this is going to be the partial derivative of f plus lambda times the partial derivative of g. And all those partial derivatives are with respect to x. When we differentiate with respect to y, similar type of calculation is done. And now, if we look at these two equations, the partial of f with respect to x, the partial derivative of capital F with respect to y, let's put those as the first and second components of a vector. And then, using the fact that these two derivatives are equal to these two things over here, we can put that into the sum of two vectors. The vector with the partial derivatives of little f with respect to x and y, plus lambda times the partial derivatives with respect to x and y of the function g. Now, this vector is just the gradient of f of xy, and this vector is just the gradient of g of xy. And so these two vectors can be represented as gradients. Now you might wonder, why didn't I represent capital F as a gradient? Well, capital F is a function of 3 variables. And so its gradient will have 3 components. But from this calculation, we're only left with a vector with 2 components here. So it's not the gradient of this function up here. This is about the only thing we can do. This vector does equal this stuff. So with what we just saw, we can rewrite the equations that we need to solve for the Lagrange multiplier method the following way. There are three partial derivative equations. They're partial differential equations in a way, where we saw how we define capital F. The partial derivative of capital F with respect to x equals 0. The partial derivative of f with respect to y equals 0. And the partial derivative with respect to lambda equals 0. Now, these first two equations we saw were equivalent to the gradient of f equals lambda times the gradient of g. This last equation is, if we take the derivative with respect to lambda of what capital F was, which is this stuff, this term does not depend on lambda at all, so its derivative is 0. This second term only depends on lambda by this multiple lambda outside, so the derivative of this term with respect to lambda is just g of xy. And so this equation becomes g of xy equals 0, which is our new constraint, remembering that we write our constraint in the form a function of x and y equals 0. So let's look at the farmer's problem one more time. Remember that in general we're trying to maximize or minimize little f with the constraint g of xy equals 0. And in this case, we'll let capital F be little f of xy, which in our case is x times y, plus lambda times g of xy, and g of xy is 2x plus y minus 4,000. Remember, we want the constraint to be in the form g of xy equals 0. So if we start off with 2x plus y equals 4,000 and subtract 4,000 from both sides, this stuff will be 0. So this is our function capital F. So then we want to solve these three equations for the partial of capital F with respect to x, y, and lambda. And all of those partial derivatives are equal to 0. This first equation just gives us y plus 2 lambda equals 0. We can see that pretty easily up here. If we differentiate f with respect, capital F with respect to x, the derivative of this term with respect to x is y, which is what we have here. The derivative with respect to x of this stuff is going to be lambda times 2 plus 0 plus 0. So you just get 2 lambda. Similarly, when you differentiate capital F with respect to y, you get this. And this equation down here, the partial of f with respect to lambda is going to be what? Well, the partial derivative with respect to lambda of xy is 0. The partial derivative of lambda times this stuff is just this stuff right here. So 2x plus y minus 4,000 equals 0. If you look at this, this is just the constraint function. The constraint was that 2x plus y had to be 4,000, so 2x plus y minus 4,000 had to be 0. So these are the same equations we saw before, and so we'll get the same solution that we had before. We'll get that x is 1,000 and y is 2,000. So wait a minute, we have overlooked an important question. The solution we got is either going to be a local minimum, a local maximum, or a stationary point. We can see this because it's basically the same situation we had in Calculus 1 for a one variable function. And this problem that we've been looking at, we can actually phrase it as maximizing a function of one variable. And so all we've done so far is find a critical point. Basically, we don't know what it is. So in our case, we looked at this problem graphically earlier, and we saw that this point 1000, 2000 for x and y actually was an absolute maximum. But the question is, how could we show that if we didn't have the graph in front of us? Well, it turns out that that's a fairly complicated question in general, especially for functions of 3 variables or more. And so what happens is, for functions of 3 or more variables, it turns out that this question takes a little bit of consideration, which we're not going to do here. You can find discussions of this in some advanced calculus books, for instance. Many times, if you look at this, you'll find that the answer to this question, do you have a local maximum, minimum, or neither, involves some linear algebra and determinants of some matrices which come from Hessian matrices. So I will leave that to you to look up if you want to. Try some advanced calculus books, or these days you can use artificial intelligence. Thanks for watching this video. I hope you found it informative and entertaining. When considering problems with more than 2 variables, the problem of maximizing a function can still be handled by Lagrange multipliers, and hopefully my next video will show that. And Lagrange multipliers in many cases is an easier method to use than just a straight onslaught on the problem trying to eliminate variables. So stay tuned. The next video is probably going to be also in Lagrange multipliers. Have a good day.